So in my first video, in the last you were seeing that the pH of buffer solution calculated on the basis of Henderson-Hasselbalch equation by taking 20 moles or 20 millimoles of salt and 10 millimoles of acid, that came out to be nearly 5.04, and that was the wrong answer. So why it was wrong? That answer is wrong because the number of millimoles of acetate ion, the conjugate base of acetic acid, available from barium acetate is 20 into 2, that is 40. And the number of millimoles of acid as usual are 10. Number of millimoles of acetic acid equal to 10. Therefore, pH of this buffer solution will be pKa 4.74 plus log salt. So be careful, salt doesn't mean salt. Salt means the number of moles or millimoles or concentration of the conjugate base available from the acid. It is log 40 upon 10. So this comes out to be 4.74 plus log 4. And this can be calculated. So this comes out to be 5.34. This is correct answer of that question. So I want to emphasize upon this point that while using Henderson-Hasselbalch equation, salt does not mean the concentration of the salt. It means the concentration in mole per liter, or the number of moles, or the number of millimoles, as the case may be, for the conjugate base of the acid or conjugate acid of the base. That's all. Now we can go for third misconception or misconcept. About the buffer solution. So this misconcept is about the selection of better or best buffer solution out of various buffer solutions given. Let us consider an example or a question. Suppose we have two buffer solutions, A and B. Buffer A is prepared by taking acetic acid and sodium acetate, 1 mole of acetic acid and 1 mole of sodium acetate. Suppose we take 1 liter solution. And the second buffer solution is also prepared by mixing acetic acid with sodium acetate. But now we have taken 0.1 mole of acetic acid and 0.1 mole of sodium acetate. Again, we get 1 liter. pKa value of this acetic acid is 4.7. So our question is, which of the two is a better buffer solution? Which is better buffer solution? You know that the pH range of a acid buffer solution is given by pKa plus minus 1. And similarly, pOH range for a basic buffer solution is given by pKb plus minus 1. It is because experimentally it is found that salt to acid ratio or salt to base ratio can be from 10 is to 1, 1 is to 10 molar ratio. That's why we have this range. You must have read that within this range, the best buffer action is found when salt to acid or salt to base molar ratio is 1 is to 1. Now we see that in the solution A as well as in the solution B, this molar ratio is 1 is to 1. So directly we cannot decide which of the two is a better buffer solution. Better means whose buffer index is more or whose buffer capacity is more. You have read that buffer capacity means the number of moles of a strong acid like hydrochloric acid or a strong base like NaOH, which must be added to 1 liter of the given buffer solution so as to change its pH by 1 unit. So let us suppose X moles of HCl be added to a buffer solution so that its pH decreases by 1 unit. The present pH is equal to pKa plus log salt upon acid, and hence this is 4.7. So new pH we want is 3.7, and we have to find out how many moles, X moles of HCl. We want to know the value of X. By adding how many moles of HCl, pH of solution A will be decreased from 4.74 to 3.7. So, when we add X moles of HCl to solution A, what will happen? Sodium acetate will react with HCl to give acetic acid and sodium chloride. Initially, we have 1 mole of sodium acetate. We are adding X moles of hydrochloric acid. It was 1 mole acetic acid in the beginning and no sodium chloride. At the end of the reaction, sodium acetate will be 1 minus X. This will be 0. That will be 1 plus X. And X moles of sodium chloride will be formed. But again, formation of sodium chloride is a material. It's not going to affect the pH of this buffer. Therefore, we can use Henderson-Hasselbalch equation as 3.74 new pH equal to pKa, that was old pH 4.74, plus log Salt upon acid. Salt is 1 minus x. Acid is 1 plus x. Or we can say minus 1 is equal to log of 1 minus x upon 1 plus x. Or log of 1 plus x upon 1 minus x is equal to log 10. Or 1 plus x upon 1 minus x equal to 10. Solving this, we get x comes out to be 0.818. That is its buffer index of a solution. Means by adding 0.818 moles of hydrochloric acid, pH of a solution will be decreased by 1 unit. Similarly, we can calculate x value for solution B. That comes out to be, we can do the similar calculation, comes out to be 0.0818, just 1/10 of the A solution. This is buffer index for solution. Obviously, we can say that the resistance power of solution A is 10 times more than the resistance power of solution B. Therefore, we can say that solution A is better than solution B. It means we should not decide a better buffer solution merely on the basis of 1:1 molar ratio of salt to acid or salt to base. We should see that which solution has largest amount of acid and salt, base and salt. On that basis, best buffer solution can be chosen, or out of the two, better buffer solution can be given. That's all about this third misconception. One more misconception I would like to discuss with you, that is about limitation of Henderson-Hasselbalch equation. Henderson-Hasselbalch equation cannot be applied in every circumstances. I will discuss why and how in my next video. Thank you. Thank you very much.